Hey, thanks for joining us for this second video in Chapter 7, where we are looking deeper into the carbocation intermediates that occur during the SN1 reaction. And one of the things you want to really keep in mind is carbocations are super needy, right? Like, because they're not meeting the octet. It's a molecule in a crisis mode. It's not just a normal cation. It's a horribly needy intermediate. So they would be willing to do sort of unthinkable things that as we'll see in today's video. So, but first, see if you can sort of rank the stability of carbocations. They're all unstable, but some are better than others, right? So, and that's gonna really tell us something about how likely it is that a carbocation might do something sort of maybe unthinkable, which is the rearrangement. And so remembering that it's very electron deficient, right? Can you think of the least stable carbocation in the world? Well, that would be the methyl carbocation. Why? Because on this carbon there's only 3 hydrogens attached to it, and hydrogens are the least electron rich element in the world, right? It's the smallest, and so there's no support or stabilization coming from the hydrogens. This is the least stable. Now, by the same logic, the next second least stable would be primary carbocations. Remember, primary carbocation means the carbocation is attached to just one other carbon. So this carbon has 2 other hydrogens on it, which is again still is not very good. So that's a very unstable. And then the next one up would be secondary carbocation, where the carbocation is attached to 2 other carbons and a hydrogen. So this is not as bad. To be fair, primary, you almost never see this in any mechanisms because it's just so unstable. Secondary is plausible. The more often than not, what you would see that's really plausible would be tertiary carbocation. Now, there's actually something that is even more stable than this. Can you think of something? And that would be resonance, right? So far, I want you to notice like this trend is based on the inductive effect argument, right? Like inductively, these carbocations have electron density donated by these single bonded carbon that it's attached to, carbons or hydrogens, and that's why tertiary is the best so far. Remember the carry rule that help us evaluate the stability of a species, especially charged species. Carry rule says that inductive effect is good, but resonance is more important, and so for that reason, something like an allylic or benzylic carbocation like this is much more stable, where this gets to share a positive charge with another carbon like that. Okay. So the bottom line here is that alkyl groups more electron rich, but resonance is better. Than inductive effect, right? And so for that, and then I want you to know these 2 species, you almost never see this. In fact, for our class, we really should not propose these intermediates, but for practical reasons, please consider them as something that doesn't exist, like a unicorn. Okay, so maybe we'll note that here. Oops. So in dissociation involved in SN1 reaction, pretty much the only things you see is secondary, tertiary, or allylic cation, which by the way this is called allylic cation. And allylic cation is not the only time that you could have resonance. For instance, if there's a lone pair, a heteroatom with a lone pair next to the carbocation, for instance, then it can have resonance stabilization as well. So hopefully that ranking makes sense to you. And that's something I want you to be able to do, is to rank the stability of species and think the carry rule. That's still very relevant. If you don't remember what that is, you might want to refer to the chapter 2 notes. That still apply. Okay. Now, like we said, because carbocation is so needy of electrons, because it doesn't meet the octet. Remember, the whole sort of purpose of our world, if you could just kind of look at it in a objective, cold way, is to meet the octet. And when a carbon doesn't meet the octet, that's a really bad situation. So what happens? Well, for instance, if this substrate does SN1 type dissociation of the leaving group, you would get this intermediate. It's a secondary carbocation. Now, which is kind of allowed, but it's not as good as a tertiary carbocation. And so for that reason, what's called the carbocation rearrangement is possible. Okay, maybe this is better. What that means is, like, you could have what's called a 1,2 alkyl shift if the structure is set up for that. And what happens after that step is, you notice one of the methyl groups, CH3, moves over with its 2 electrons. So that means this carbon here is left with a carbocation, whereas now this carbon fully meets the octet and no charge, right? And then, like, this could go through some solvolysis or what have you, and maybe if the solvent you're using is water, you could end up with a product like that after a couple steps. And this is all driven by the fact that tertiary is much more stable than secondary. Okay. And another example of this version of this is to alleviate some other uncomfortable situation, like strain or torsional strain or angle strain, such as experienced by the cyclobutane. And if this guy undergoes dissociation, you would end up with this carbocation that has an empty p orbital on this carbon, right? That's why it's positively charged, and it's experiencing, remember, empathy with the organic molecules, right? That would help you with organic chemistry. So this guy, if you build a molecular model, you'll notice there's torsional strain because the CH bonds and whatnot are all eclipsed, mostly eclipsed, and then of course there's an angle strain. So this is really uncomfortable. Now, carbocation is like such a destabilized situation that almost anything goes. It's kind of like, right, like it's a chaotic situation when a new nation is born or something, right? Like almost anything goes to find a more stable situation. And so this alkyl group could migrate. And I want you to notice that it's the only alkyl shift that's possible is 1 2, as in like from position 1 to 2, like the next door. That's the only possible shift. Okay, and that would give us this intermediate, which is still secondary, but you know, let's say the solvent you're using here is methanol. This is very unstable, but this is not as bad as that guy, and so for that reason this intermediate can hang around longer, and if it hangs around long enough it encounters the solvent nucleophile and it eventually becomes the product. In this case it should look like that with the methanol, right? Here the driving force is to alleviate the strains. Okay. Now, one other thing I should, well, maybe I'll talk about that later. So, yeah. One other type of shift that we could observe is 1,2 hydride shift. Okay. And the hydride, of course, is this species. Hydrogen with 2 electrons on it is a hydride. Remember, "ide" always means a negatively charged ion. So that might happen with a substrate like this. As an example, after the dissociation step, you would end up with, maybe that's not, this secondary carbocation. Now, this, if it wants to become tertiary, I remember empathy with the molecule. If you put yourself in the shoes of this guy, this is a secondary carbocation, very needy, and it's so reactive. If it can become a better carbocation, more stable carbocation, it would try to do that. And in this case, there actually is such an opportunity, because if you move the methyl group from here to there, I want you to notice how the resulting carbocation here will be secondary again. So that's not any improvement. But if the hydride moves over, this is not a movement of proton, I want you to notice, because with this arrow I'm saying that this hydrogen is taking these 2 electrons and it's making a new bond with this carbon. And what happens after that, of course, would be this carbocation, which is tertiary, right? This carbon had 1 hydrogen, now it has 2 hydrogens. The second was that hydride that shifted. Okay, so I hope that makes sense. And this becomes whatever, right? So what's the sort of take home here? The take home is if rearrangement is beneficial, it will occur. So again, I can't stress enough the importance of the skill to be able to judge or evaluate the stability of different species intermediates. Now, in general, I want you to know that this pretty much only happens once, mainly because usually carbocations don't have enough time to do a bunch of rearrangements. It's so reactive that it will eventually react with the solvent that it's surrounded by, right? So, and what I mean by that is, like for instance, this intermediate. If you're pretty sharp, right, like you might have wondered, well, there is a hydrogen over here, and if that does a hydride shift, it can become a tertiary carbocation. So shouldn't the substitution happen right here? That's a very good question, and that is technically plausible, maybe possible, but as we said, the carbocation, even if it's tertiary, let's say, it's so reactive that it will react with the solvent immediately. The reason why this rearrangement happens is the original structures like these are so unstable that these shifts happen faster than these reactive electrophile bumping into the nucleophilic solvent. So hopefully that makes sense. Another thing I want to point out is the reaction arrows that we used. Here I deliberately used the equilibrium arrow, whereas this is not equilibrium. So you might have wondered about that, and that is kind of on purpose. This implies that that step is irreversible. So this is normally an irreversible step. Maybe I'll say this means irreversible. Whereas this arrow, of course, implies it's reversible. It's an equilibrium step. And that's what we did in this reaction mechanism earlier as well. This is, in general, should be a reversible bunch of steps, except for the rearrangement. Okay. Yeah. And we know that this is reversible. These are reversible because in the reverse direction, it's actually, like for instance, this step, it's easier for this carbocation to become the starting material because it's higher energy. It always wants to go down in energy. So reverse is definitely possible. Here the reverse is a little bit harder. It's a little higher activation energy it would have to overcome, but both of these are high enough energy that like there's not that much difference, so it's still plausible. It's possible to go in the reverse. Same with this. So that's why we're using these reversible signs, arrows. But here it's there's no pretty much way for the tertiary carbocation to become secondary in the reverse because the energy difference is so vast. Same with this strains. Okay, so hopefully that makes sense. The last thing we want to say about the carbocation is intermediate is it has an impact on the stereochemical outcome. If we think about this potential SN1 setup, what would be the product? Well, let's think about the mechanism to be able to predict the product, which is really an important thing that you want to be able to do in this class. Basically, starting at this point, probably through the end of the school year, including the second semester, being able to predict the reaction products, that's going to be one of the most important skills and type of problems that you're going to see throughout our class and on exams and so forth. Predict the product. Okay, so in fact, the second exam and third exam, as well as the ACS final exam, that's going to be a big chunk of all those exams. Predict the product. Okay, the way you should do that is not just to stare at this for very long, but to think through the mechanism. Okay, so this guy is tertiary, which means it's pretty prone to being for solvolysis, where the good leaving group could leave, right? And if that were to happen, you would get this tertiary carbocation, which should tell you that there is no rearrangement here. Okay, that's how I know. If you ask how do you know if there's going to be a rearrangement, especially if you have a tertiary, there's no way it's going to do rearrangement. Now, that this would be intercepted by our nucleophilic solvent. It's a poor nucleophile, but it's nucleophilic enough. Now, I want you to notice that the geometry of this is trigonal planar because it's an sp2 carbon now. Why does that matter? Well, because this nucleophile could attack either from the back end or the front side of the molecule, right? Because this is now a flat species, at least around this carbon. So let's think about the two pathways, right? So let's say if it happens from the back, or if it happens from front of the carbocation. So then if it happens from the back, right, the methyl group would be pushed up front, and then the methanol would be connected back there to alleviate this cationic oxygen's charge, right? Like proton can come off. You can't easily break an oxygen carbon bond, but oxygen hydrogen bond, on the other hand, that's easily broken, especially when it's acidic like that, oxonium ion cation. The most likely base is going to be the solvent that has these lone pairs. So if that happens, right, the product is going to be this species. And then if the reaction happens from the front, right, then here's your methanol. The same ordeal. That would give us that compound. And do you notice these two are enantiomers of each other? Mirror images of each other. And because this is completely flat, what are the chances of the nucleophile attacking from the back as opposed to the front? And it should be 1 to 1. And that means at this point you should end up with racemic mixture or racemate. So the products are going to be just gonna kind of cheat here. Do that. Well, the product should be this racemic mixture. And so that's typically the rule of thumb for SN1 reaction, or in our class you could just assume that SN1, if the SN1 reaction happens at a chiral center, which that's why we picked this example, that's a chiral center, you should end up with a racemic product. Okay, hope that makes sense. All right, see you in class.